functions with multiple boundaries and Weil-Petersson volumes. Okay.
Okay, so thank you for the introduction. So in this talk, I'd like to discuss the large genus asymptotic expressions of Weil-Petersson volumes and computational correlation functions in JT gravity. I'd like to thank the organizers for giving me this opportunity to give a talk at this conference. And this talk is based on these two papers. And here's a plan of this talk. So firstly, I'd like to briefly review JT gravity. Then I will discuss review partition functions and some correlation functions in JT gravity and the volume of the moduli of Riemann surfaces, which is known as Weil-Petersson volume. And then I'd like to discuss Mirza-Kani's recursion relation and the Weil-Petersson volume. Then I will discuss asymptotic formulas for the Weil-Petersson volumes. Then finally, I will discuss computation of correlation functions in JT gravity. So let me state the themes of this talk. The volume of the moduli of hyperbolic Riemann surfaces, which is known as the Weil-Petersson volume, plays an important role in computing partition functions and correlation functions in JT gravity. And there are two themes of this talk. And one theme is to yield large genus asymptotic formulas for the Weil-Petersson volumes when the genus of Riemann surface is large. And the second theme is to evaluate higher genus contributions to the correlation functions in JT gravity, utilizing the large genus asymptotic formulas of Weil-Petersson volumes. Firstly, I'd like to briefly review JT gravity. Jackie Teitelbaum gravity is a two-dimensional gravitational theory on hyperbolic Riemann surfaces. And when Riemann surface S has one or more asymptotic boundaries, the computation of path integrals in JT gravity, in essence, reduces to two parts. And one part is an evaluation of the volume of the moduli of Riemann surfaces with the topology of S. And the other part is evaluation of path integral over the wiggles or quantum fluctuations along each of the asymptotic boundaries. And JT gravity is a two-dimensional gravitational theory with graviton and the dilaton. And the action of JT gravity is given by the following action. In this action, the second term fixes the curvature to be -2, and third term is a boundary action. So the action indicates that the solutions in J2 gravity are hyperbolic surfaces, namely the surfaces with negative constant curvature, R is -2. And one can decompose a Riemann surface with a wiggle or quantum fluctuation into a Riemann surface with a geodesic boundary and a trumpet connecting the geodesic boundary and the wiggle along an asymptotic boundary, as discussed in the paper by Sardchenko and Stanford in 2019. And wiggles along the boundaries of the Riemann surfaces in J2 gravity are controlled by one-dimensional Schwarzian theory. And because SYK models are described by one-dimensional Schwarzian theory at low energies, this relates J2 gravity to SYK models. In this talk, however, we'd like to focus on Riemann surfaces with geodesic boundaries and the volumes of their moduli. And we do not focus on the wiggles and the theories along the wiggles in this talk. And then I'd like to mention how partition functions and correlation functions can be evaluated in J2 gravity and how they are related to the volume of the moduli of Riemann surfaces. A correlation function in J2 gravity has following genus expansion. And as discussed in the paper by Sardchenko and Stanford, genus G partition function with n boundaries is actually given by the following integral. Here, genus G partition function means genus G term in this genus expansion of the correlation function. And here in this expression, V of Gn denotes the volume of the moduli of hyperbolic Riemann surfaces of genus G with n geodesic boundaries of lengths B1 up through Bn. And this volume is known as a Weil-Petersson volume in mathematics. So, and Z trumpet denotes contribution from the trumpet geometry connecting geodesic boundary and asymptotic boundary.
Just a question here. What is beta? Beta J? What is beta here?
Oh, beta?
Yes.
Oh, that's their parameters, parameterizing the lengths of the asymptotic boundaries of Riemann surface.
Okay.
So computing partition functions and correlation functions in J-D gravity, in a sense, boils down to computing the Weil-Petersson volume, VGN. And because we focus on the large genus asymptotics of the Weil-Petersson volumes in this talk, I just yield higher genus contributions to the correlation functions in J-D gravity. So our computation in this talk is contributions from all genera that are larger than some fixed number, say G0. So as we will discuss in section 5, we give higher genus contributions of genera G such that they are larger than some number G0. And contributions from the trumpet geometry connecting an asymptotic boundary to a geodesic boundary of a Riemann surface was computed in the paper by Sadchenko and Stanford. That's an expression shown in the slide. So the contribution to the correlation function in J-D gravity can be obtained once Weil-Petersson volume is computed. Then I'd like to move on to discussion of Mirzakhani's recursion relation and Weil-Petersson volume. Mathematician Mirzakhani discovered a method to compute the Weil-Petersson volumes for any genus G and any number of the geodesic boundaries N recursively. This method was discussed in her paper in 2007. The Mirzakhani's recursion relation formula looks like this. And we are not gonna go into the details of this formula, but the left-hand side is actually is a partial derivative with respect to one of the geodesic lengths of the boundaries. And the formula gives a recursion relation of the Weil-Petersson volumes. And an important point of this formula is that the terms on the right-hand side are functions of Vg prime m, where G prime is strictly less than G, or M is strictly less than N. So using Mirzakhani's recursion relation, one can compute the Weil-Petersson volumes recursively. So owing to Mizukani's recursion formula, one can compute the volume VGN from VG prime M, where G prime is structurally less than G recursively. However, there is a complication in the formula, and that's the terms on the right-hand side in the recursion relation involve volumes whose numbers of the boundaries M are strictly larger than N. So you need to know some volumes with more numbers of the boundaries, but less general, to compute the Weil-Petersson volumes with higher general in this formula. And in principle, one can recursively compute the volume VGN for arbitrary genus G utilizing Mizukani's formula. However, performing this computation practically becomes hard when the genus G becomes large and the number of the terms involved in the recursion computation grows rapidly. So the computation of the volume becomes difficult when the genus G of a Riemann surface becomes large. And I would like to also mention a relation to Witten's conjecture. And JT gravity is due to a matrix integral as discussed in Charles, Schenker, and Stanford. And JT gravity can be viewed from the matrix integral perspective. In this correspondence, Mizukani's recursion relation corresponds to Einard Oranton's topological recursion, as discussed in the paper by Charles, Schenker, and Stanford in 2019. And this correspondence can be viewed in the context of Witten's conjecture, which is conjectured the equivalence of two versions of two-dimensional quantum gravitational theories. And one is intersection theory of line bundles on the moduli of Riemann surfaces, and the other is a double-scaled matrix theory. Witten conjectured that the two theories must be equivalent, and this is known as Witten's conjecture. And the conjecture was proved by Koncevich in 1992. And Mizukani also gave a proof to the conjecture utilizing recursion relation of Weil-Petersson volumes. Then I'd like to move on to asymptotic formulas for the Weil-Petersson volumes. So now in this section, I'd like to discuss some explicit evaluations of Weil-Petersson volumes. And when genus G becomes large, when genus G of a Riemann surface becomes large, is it possible to estimate the volume, Weil-Petersson volume VGN from Mirzakhani's recursion formula directly? Assuming that the genus G is very large, this is very difficult owing to the following reason. And the problem is that one wants to compute VGN from VGN, where m is smaller than n, but VGN -1 and n+1 boundaries inevitably appears in the Mirzakhani's recursion formula. So in the region where the genus of a Riemann surface is large, direct application of Mirzakhani's recursion formula does not easily yield large genus asymptotic formulas for Weil-Petersson volumes. So this is a complication when one wants to compute large genus asymptotics of the Weil-Petersson volumes. And so owing to this difficulty, I tried something else. Instead, one can use the partial differential equations that fold for Weil-Petersson volumes as proved by Du and Norbury. So here are these two equations are partial differential equations satisfied by Weil-Petersson volumes proved by Du and Norbury. And on the left-hand side, partial of n+1 is a partial derivative with respect to n+1's boundary of a Riemann surface. And the value 2 pi I is plugged in for Bn+1. And the first term on the right-hand side of the second equation, partial j is a partial derivative with respect to the parameter bj of the volume. So studying these two partial differential equations, one can find that the two partial differential equations in fact impose strong constraints on the behaviors of the Weil-Petersson volumes VGN. And applying these two using the two partial differential equations, I estimated large genus asymptotics of the Weil-Petersson volumes. Using a method that is different from applying the differential equations by Du and Norbury, the asymptotic expressions for Weil-Petersson volumes without a boundary and with one boundary, VG1, were estimated by Sarchenko and Stanford when genus G is large. They applied matrix integral reasoning and recursion technique to estimate the values of these volumes without a boundary and with one boundary, VG0 and VG1. And here B denotes the length of the geodesic boundary. And one can confirm that their asymptotic expressions indeed satisfy the partial differential equations by Du and Norbury, which is a non-trivial consistency check of the result. And I applied the differential equations by Du and Norbury to the volume VG1, Weil-Petersson volume with one boundary obtained in Sarchenko and Stanford to estimate asymptotic expressions for Weil-Petersson volumes with multiple numbers of boundaries, VGN, for any number of the geodesic boundaries. So for example, for VG2, with two boundaries, I obtained the asymptotic expression for VG2 of B1 and B2, and B1 and B2 parameterize the lengths of the geodesic boundaries of a Riemann surface under the condition that genus G is much bigger than the geodesic lengths B1, B2, and also genus G is assumed to be large. And the first term on the right-hand side, it's a leading contribution. And the second term is a subleading contribution to the Weil-Petersson volume. And I expect that there are some other subleading terms. But the major contribution is given by the first term in this expression, which is a product of Singe functions And in a similar fashion, I also obtained the expression for Weil-Petersson volume with 3 boundaries, VG3. Under the condition that the genus G is much larger than the lengths of the geodesic boundaries B1, B2, and B3. And also the genus is large. Then the main major contribution to the Weil-Petersson volume for large genus asymptotic is given by this term, which is a product of Sinch functions. And I also expect some subleading contributions to asymptotic Weil-Petersson volumes. So in summary, we estimated the asymptotic Weil-Petersson volumes of the moduli of the Riemann surfaces with multiple numbers of the boundaries when the genus G of a Riemann surface is large. So finally, I'd like to discuss an application of the obtained large genus asymptotics of the Weil-Petersson volumes to correlation functions in J gravity. Because genus G partition function ZGN within the boundaries is given by the following formula, as in the paper by Sarchenko and Stamford. So the genus G partition function is obtained as an integral over the Weil-Petersson volume and also times contributions from trumpet geometries connecting the geodesic boundaries of a Riemann surface with asymptotic boundaries. And the contribution from the trumpet connecting an asymptotic boundary and a geodesic boundary of a Riemann surface is given as the term shown in the slide. Higher genus contributions to the correlation functions can be computed from the large genus asymptotics of the Weil-Petersson volumes. Oops. And a large genus asymptotic Weil-Petersson volume I estimated the large genus asymptotic Weil-Petersson volume, VGN, with n boundaries. That is shown in the slide. I only indicated the leading contribution in the genus G, and that is proportional to gamma function and also a product of sinh functions. Oops. And because of this formula, when VGN is plugged into this formula, then one can evaluate the genus G partition function in the genus expansion of the correlation function. And the computational result is shown in the slide. And the computation only makes sense in the region where genus G is large. And because I used large genus asymptotic Weil-Petersson volumes, this method works only for terms with large genus in the genus expansion of the correlation function. And summing over all genera that are large enough, say for genera such that they are larger than G0 for some G0, one obtains higher genus contributions to the correlation function with n boundaries. Okay, so I'd like to give a summary of this talk. Correlation functions and partition functions in JT gravity can be computed using the Weil-Petersson volumes, VGN. And the volume, in principle, can be computed via Mirza-Khanis recursion relation. However, computing the Weil-Petersson volume practically becomes very difficult when the genus of a Riemann surface becomes large. And to avoid this difficulty, we used partial differential equations by Du and Norbury to yield asymptotic expressions, I mean, large genus asymptotics of the Weil-Petersson volumes. And the asymptotic volume formulas are used to yield higher genus contributions to the correlation functions in JT gravity. Okay, I stop here. Thank you.
So many thanks for your talk. Any questions from the audience? No questions. I know about this double gravity and JT gravity is of interest of some of the participants in the conference, but they haven't shown up. Like Daoud Moumni, he worked in this subject in the last, I think, couple of years. So, but unfortunately, he's not around. So, any questions from the audience again? No. I was just wondering whether there are some applications to this JT gravity and in general 2D gravity. Is there any application that can be done?
Oh, application of JT gravity.
Yeah, in terms of cosmology, for example.
Cosmology.
Well, not the JT gravity, but I think in your first slide you have shown something about 2D, two-dimensional gravity, if I'm not wrong. In your first slide, I think.
Okay. Do you mean this slide?
Here, this slide, yeah.
Oh, I am not sure about an application to cosmology.
Okay. Okay, anyway, so in that case, if no further questions, then I think we can stop here and thank Kimura again for his nice talk. So now I think we can move to the next talk.